Welcome to Cambridge IGCSE Physics, Lesson 42.1, Current in Parallel Circuits. Today we explore how electric current behaves when it flows through parallel branches in electrical circuits. This is core content for your Cambridge IGCSE Physics qualification, Syllabus 0625. Understanding parallel circuits is fundamental to electrical engineering and everyday electronics. We will examine how current splits at junctions and divides between different branches. This knowledge applies to household wiring, electronic devices, and electrical safety systems worldwide. Let's examine our learning objectives for today. By the end of this lesson, you will be able to, first, state that current from the source is larger than current in each individual branch. This is a fundamental principle of parallel circuits. Second, understand that current splits at circuit junctions. When current reaches a junction where the circuit divides, it separates into different paths. Third, know that current divides between parallel branches according to their resistance. These objectives align with Assessment Objective 1, which focuses on scientific knowledge and understanding. Each objective builds your foundation for understanding electrical circuits. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, parallel circuit, which means components are connected across common points, creating multiple paths for current flow. Unlike series circuits where components connect end-to-end, parallel circuits provide alternative routes. Second, current splits, which means current divides at junction points where the circuit branches. The total current entering a junction equals the total current leaving. Third, branches, which means separate paths in parallel circuits where current can flow independently. Each branch operates independently of others. Understanding these terms precisely is crucial for Cambridge IGCSE success. Let's explore our first core concept, current conservation at junctions. The fundamental principle states that current entering a junction equals current leaving that junction. This is Kirchhoff's current law, named after German physicist Gustav Kirchhoff. The definition is, at any junction point in a circuit, the total current flowing in equals the total current flowing out. Mathematically, we express this as I total equals I1 plus I2 plus I3, where I represents current measured in amperes and subscripts indicate different branches. The diagram illustrates this principle clearly. Notice how 3 amperes enters the junction from the battery, then splits into 1 ampere through lamp 1 and 2 amperes through lamp 2. The total remains 3 amperes. This principle is fundamental because it reflects conservation of electric charge in circuits. Now we examine the experimental method for measuring current in parallel circuits. This follows Cambridge IGCSE practical requirements. The apparatus needed includes a battery or power supply for electrical energy, lamps as resistive components, ammeters to measure current, and connecting wires for circuit construction. The method consists of these steps. First, construct the parallel circuit with components connected across common points. Second, connect ammeters in series with each branch to measure individual currents. Third, connect 1 ammeter in the main circuit to measure total current. Safety is paramount. Use low voltage supplies, typically 6 volts maximum. Check all connections before switching on. Avoid short circuits which can damage equipment. The diagram shows the complete setup with ammeter A0 measuring total current, A1 measuring current through lamp 1, and A2 measuring current through lamp 2. Let's work through our first example. The problem states, in a parallel circuit, lamp 1 draws 2 amperes and lamp 2 draws 3 amperes. Calculate the total current supplied by the battery. We are given current through lamp 1 equals 2 amperes, current through lamp 2 equals 3 amperes. We need to find the total current from the source. Step 1. Write the equation. We use Kirchhoff's current law, which states I total equals I1 plus I2, where each I represents current in amperes. Step 2. Substitute the values. We write I total equals 2 amperes plus 3 amperes. Step 3. Calculate the result. 2 plus 3 equals 5. Step 4. State the answer. The total current is 5 amperes. This demonstrates that parallel circuits draw more total current than individual branches. Example 2 applies current conservation to analyze circuit behavior. The problem asks us to analyze current distribution in a 3-branch parallel circuit. The data shows total current equals 6 amperes, branch 1 current equals 2 amperes, branch 2 current equals 1 ampere. Now we analyze systematically. First, apply Kirchhoff's current law. The total current must equal the sum of all branch currents. Second, calculate the third branch current. Since 6 amperes total minus 2 amperes minus 1 ampere equals 3 amperes, branch 3 carries 3 amperes. Third, verify the conservation principle. 2 plus 1 plus 3 equals 6 amperes, confirming our calculation. Fourth, compare branch currents. Branch 3 carries the most current, branch 1 is intermediate, and branch 2 carries the least. The bar chart shows this distribution clearly, with each branch contributing to the total current supplied by the source. Mathematical skills are crucial for parallel circuit analysis. Let's examine 3 essential skills. First, current addition for multiple branches. When we have n branches where n represents any number of parallel paths, the total current equals I1 plus I2 plus all remaining branch currents up to IN. Always include units in every calculation step to avoid errors and earn full marks. Second, finding unknown branch currents. To find an unknown current Ix, we rearrange the current law equation. Ix equals total current minus the sum of all other known branch currents. This algebraic manipulation is essential for problem solving. Third, percentage current distribution analysis. To find what percentage of total current flows through each branch, we calculate branch current divided by total current, multiplied by 100%. This skill helps analyze circuit efficiency and component loading. Now practice what you've learned with these 3 questions. Question 1 is basic level. It asks, 2 parallel branches carry 4 amperes and 6 amperes respectively. Find the total current supplied by the source. This tests direct application of current addition. Question 2 is intermediate level. It states, the total current is 12 amperes. Branch 1 carries 5 amperes. Find the current in branch 2. This requires you to apply current conservation by subtraction. Question 3 is advanced level. The question is, 3 branches carry currents in the ratio 2 to 3 to 5. The total current is 20 amperes. Find each individual branch current. This tests your analytical skills with ratios and proportional reasoning. For all questions, remember to show you're working clearly, include units in every step, and check your answers make physical sense. Write your answers now before looking at the solutions. Physics principles power our modern world. Let's see how parallel circuits apply in practice. In household wiring, parallel circuits allow multiple appliances to operate independently. Each device receives full voltage and can be switched on or off without affecting others. This is why lights continue working when you turn off the television. In vehicle electronics, car lights operate in parallel for safety reasons. If one headlight fails, the other continues working. Brake lights, indicators, and dashboard lights all use parallel connections to ensure reliability. In computer systems, parallel connections distribute power efficiently to different components. The motherboard, hard drives, and cooling fans all receive power through parallel branches, allowing independent operation and better system reliability. These applications show why understanding parallel circuits matters for careers in electrical engineering, electronics design, and power systems engineering. Let's review the solutions systematically. For question 1, the answer is 10 amperes. We add 4 amperes plus 6 amperes to get 10 amperes total current. This demonstrates direct application of current addition in parallel circuits. For question 2, we find 7 amperes in branch 2. Using current conservation, 12 amperes total minus 5 amperes in branch 1 equals 7 amperes in branch 2. This shows how to find unknown currents using subtraction. For question 3, we use ratio calculations. The ratio 2 to 3 to 5 has 10 total parts. Each part represents 20 amperes divided by 10 equals 2 amperes. Therefore, branch 1 carries 2 times 2 equals 4 amperes, branch 2 carries 3 times 2 equals 6 amperes, branch 3 carries 5 times 2 equals 10 amperes. Check 4 plus 6 plus 10 equals 20 amperes total. Now exam success tips. First, always show you're working step by step. Even if the final answer is wrong, you earn marks for correct method. Second, include units in every calculation step. Third, check if your answer is reasonable. In parallel circuits, total current must always exceed individual branch currents. Fourth, read questions carefully to identify exactly what is being asked. Let's summarize today's lesson on current in parallel circuits. The key points to remember are, first, current conservation principle. The total current from the source always equals the sum of all individual branch currents. This reflects the fundamental law of charge conservation in electrical circuits. Second, the junction rule, also known as Kirchhoff's current law. At every junction point where circuits branch or merge, the current flowing in must equal the current flowing out. This principle enables us to analyze complex circuit networks systematically. Third, practical applications. Parallel circuits enable independent component operation, which is why they are used in household wiring, vehicle electronics, and computer systems worldwide. For further study, review Kirchhoff's current law and practice applying it to different circuit configurations. Work through additional current calculation problems to build confidence and speed. The next lesson covers voltage in parallel circuits, which builds on today's current analysis by examining how voltage behaves across parallel branches. Understanding both current and voltage behavior is essential for complete circuit analysis.